Hello, good morning or good afternoon, everyone. I'm Ken Biba, and I'd like to invite you to listen to my thoughts on this moment in time where I think there's two revolutionary technologies that have come up in 3D printing and in modern electronics and software that give us a unique opportunity to transform amateur rocketry to a whole new stage. So I will not have access to chat and Q&A during the presentation, but right afterward, I'll go through all the questions. So please go to the Q&A session and put your questions there, and I'll get to them. As soon as I finish. So, as I said, my talk today is combining these two ideas of 3D printing and Moore's law, which I mean by what's happening in electronics right now, to give us yet more revolution on amateur rocketry. And my theme is about making impossible things. I'd given a presentation earlier today, very focused on HPR and 3D printing. This will also include some of that material, but we'll extend it to looking at electronics and communications and telemetry, and suggest a couple of projects that I've been working on that include all these pieces and wouldn't be possible without them. And so let's get to it. So if you haven't heard me before, this is me. I ended up having a career not as an astronaut, though I wanted to be, as a physicist, computer scientist, and ultimately entrepreneur. Remember that I had something to do with the creation of Wi-Fi cable modems and computer security. I've now been lucky enough to be 30 years in amateur rocketry, maybe a little longer. Memory gets a little tough. I'm a level A guy and ham and been a tap, been on boards, altitude records. I put my own satellite up. That's actually, we'll see a picture of that. And I'm very passionate about using rocketry as a vehicle for seducing adults and students of any age to think about STEM and really the fun of both making things and making things that go fast that enable us to learn about the world. So again, as you guys know, I'm very much about a point of view. 30 years ago, I learned amateur rocketry with cardboard and plywood. I was reflecting on, I think, Todd Schwine's photo, which has him with a lock graduator. And I think that was my first rocket too. And then I moved about 20 years ago into fiberglass and carbon fiber. I was lucky that I was mentored in doing vacuum bagging by a guy whose business was building F1 race cars. And that was kind of cool. But it was with chemical delay recovery deployment. And now today, I do everything. But one of the things we learned from my career in software, and many of you have probably been in software as well, and we see every day with SpaceX, that iterative deployment is a good thing. If we can make our best effort to try a first touch and test it, and it fails, we learn from that failure. We don't learn from success, we learn from failure. And to iterate that by failing less, we begin to build a much better product. And so 3D printing and the modern way we can build electronics and the electronics allows rapid iterative development of modern rockets, makes them accessible and cost effective. And in fact, my discovery is that it's probably less expensive today to build this kind of rocket than it is, buying stuff off the shelf with carbon fiber and certainly fiberglass. So let me first talk a little about 3D printing. If you happen to listen to me a few hours ago talking about 3D printing, some of this will be a repeat. Please don't ask more questions. 3D printing basically makes hardware like software, which means that we can imagine it, we can write it, we can iterate it, and we can print anything right now. It's only cost and scale. Amateurs like us can't really print metal and concrete, but we can print plastic and composites. Though it's very interesting as I follow the industry right now. Clearly, in professional rocketry, we're printing metal. You know, if you look at a company like Relativity, they're printing entire rockets, including uh, motors, structures, everything. And we're now finding housing being constructed out of concrete using 3D printers that in fact is more cost effective because it's faster. And for us, I think in amateur rocketry, it's only a question of time when it's useful. So I asked the question of why bother? Why is 3D printing important? Well, here's a project I did 15 years ago. I fly for the last 20 years with ARLISS, in which we make 6-inch diameter, 8-foot rockets flying on M motors and launch student satellites up to about 10,000 feet. And those rockets are cool. They fly subsonic. They're all about 30 or 40 pounds dry. And then it's interesting to see how they perform differently. And so one of the things I learned as I began to learn more about aerodynamics was, well, how could I make it better? So subsonic rockets generate drag largely by skin friction. And so if you have less surface area, you have less friction. And that involves making a smaller nose cone and a bit smaller boosters. You can see with this system I made here. And lo and behold, when I flew it, it went about 50% higher. So rather than going about 10,000 feet, it went to about 16. And this is now the version I just finished making, in fact, this month. This is also a 6-inch nose cone. It carries a 2U CubeSat, which you can see kind of laying horizontally there between the tip of the nose cone and the bulk of the nose cone. It's made in sections that screw together. And this can be deployed either carrying it passively as a captive deployment, or it can be an active deployment at apogee. This probably costs me $50 in filament to put together. Because it has less mass and less surface area and less drag, it will probably cost, to get to the same altitude, probably half the motor cost. So your project can perform better. You get the customized aerodynamics. It's a little hard to see, but you can see the nose cone tip in the lower right-hand corner there. I tuned that by finding a power series shape that gave me the best performance. So we can tune nose cone shapes in a way that we can't buy them. We can build integrated fin cans in ways we can't buy them. And in many ways, since I've been doing vacuum bagging of whole fin cans, let me tell you, it's a lot easier. And now we can think about building parts in mechanical pieces that we can mechanically assemble. And lastly, we can learn more. We can learn more about the aerodynamics, like this is customized to the particular shape that gives the least drag. And we can think about more detail about strength rather than buying parts off the shelf, or to my mind, building them out of things like fiberglass sheet or plywood. Now we can begin to think about the shapes and structures in a very more customized manner. So some 3D printing basics quickly. The core thing is strength of materials, and the things that we trade off, I think, are rigidity. And too much rigidity is not a good thing. You really want some flexibility. Axial strength along the line of thrust. And I find that materials that give us some impact resistance I think are stronger. They're less fragile. Second biggest thing is the glass transition temperatures. When does heat deformation of the plastic begin? And this happens at a wide variety of temperatures, actually, depending on the plastic. And that drives us to material selection. This became important when I really discovered, had the insight beaten over my head, is that the materials we use in the things we think are very strong and very powerful, like composites, like carbon and fiberglass, they're bonded together with epoxy resin. But epoxy resin has a glass deformation, has a heat deformation temperature of about 70 degrees C. It turns out our best material, some of our pretty good materials for 3D printing, like PETG, things like enhanced PLA, sometimes called tough PLA or PLA plus, much less nylon, have that deformation temperature or higher, it's about 100 degrees higher. So we essentially can build stuff that is as strong and temperature resistant in many ways as the things we think about in composites. And then we can tune how we design it by the mechanics of the workflow. So What we do is called fused deposition modeling, FDM. It's layers of extruded plastic. Here, it's printing out actually the tip of that 6-inch nose cone you saw. These printers precisely squirt melted plastic, depending on the material, somewhere between 200 and 300 degrees C, with a resolution of about 0.05 of a millimeter on a nozzle diameter, which is really the smallest feature size we can really describe, of about 0.4 millimeters. We have a choice of materials, and we have a whole software workflow tools that allow us to easily design this as we would design software and then print it out as we would print a material. This process is essentially iterative design. It looks like software, which means that we can test it, try it again, modify it, describe how it fails, make it better. So strong materials, what we want to try to get rid of is using materials that cheap printers do, which is PLA, which is great for toys, not so good for rockets. Materials I happen to like is something called PETG and something called PLA Plus, which is an enhanced PLA for strength. It has roughly the same properties as ABS. And then nylon. And I'm particularly fond of PETG because it has some flexibility. And it's really, it's a very high quality print. Nylon would be my next choice, which is very high, very hot, very strong, very temperature resistant, a little harder to print, takes a little more work, better printer. But then you can enhance those materials with additions. You can impregnate it with powdered carbon fiber fiberglass, or for real strength, you can impregnate it with a continuous carbon fiber embedded. And there's a particular company called Markforged that builds this filament and customized printers to do that. And essentially, they think that it's strong as aluminum, certainly in some directions. You can then print it for fun with materials like colors, fluorescence, wood, and metal fabrics. We have flexible materials. Down in the lower picture, you can see there's a tube on the left. That's my satellite, OpenSat, which went up last part of 2017. It was at part 2 satellites and a common 2-sat deployer. And in this case, we prototyped it in PLA. We did all the development in PLA, and then we sent the design out to an outsource firm that printed it in a different technology called laser sintering. And so that's basically a carbon fiber container, and it's called WinForm, and space capable. So as we think about rocketry properties, we think about strong and flexible impact resistance. We think about temperature resistance. And that gets us to materials particularly like PETG and nylon. So what are the limits of this technology? Its weight. It's generally heavier than balsa wood and paper, particularly for small rockets, but lighter than fiberglass. I find that as I build more, particularly HPR rockets out of it, they're actually lighter and faster. Size. Most of these parts are limited in size, the size of the print volume of the printer. Thank God there are bigger printers. It's a way to spend more money over time. Strength, we need to look for, only the best materials are as good as aluminum, but many materials are as good as composites, particularly in terms of temperature resistance and flexibility. But I think I'm particularly fond of PETG as being good enough for almost all missions. And I would refer you to my pitch about HPR to look at some of my HPR projects up to M mode, give you a better idea. Temperature, it's that PETG and PLA. Nylon is much better, and it can take time. A fin can take a day or two. So the printing workflow is that you do a system design using tools we've always used, OpenRocket, RockSim, or RAS-Aero. We then break down individual components. Generally, right now, I'm finding building tubes is not cost effective in any 3D printing, and so I use composite tubes, fiberglass. But I then build nose cones, transitions, recovery bad bays, and fin cans using tools like Tinkercad, which is really simple for guys like me that are really not mechanical engineers, and Fusion 360, which would be the big daddy. And then I strongly recommend that you download and use OpenSCAD. It's an open source tool that allows for programming 3D objects. Most importantly is not OpenSCAD itself, unless you really want to get geeky about building programs, is there's a wide variety by very well competent designers. I get mine off Thingiverse, and you can look for OpenSCAD libraries for rocketry. But there's good libraries for building things like nose cones, fins, fin cans, transitions, interstages. And those give us the basic components that we can then take back and integrate into that we can then build complete parts. Then output to a program called the Slicer. I use Simplified 3D, but Cura is the open source one that comes with most printers. And this basically translates from the 3D space automagically into instructions to laying out those layers we saw in the printer. This is a very interesting, and much of this, I think, comes from the same technology we use to lay out PC boards. We're seeing, I think of this as an expert system in many ways. And lastly, we ship it to the printer. I started with a Creality, which was real cheap. I found that one of the values of being real cheap is that it became the hobby rather than me using it as a tool. So I gave mine away and got a Dremel, which is a prosumer one. It does many materials. It kind of auto calibrates itself. So it really is, just like many Dremel tools that I use, a high quality instrument that I use rather than a hobby in itself. And then lastly, I mentioned Mark Forged, which is more expensive than many people want to spend. Thank God I have a friend that had invested in one, but it prints nylon plus embedded carbon fiber to print things almost like aluminum. The cool thing is you can then iterate, just like we do with software, and it doesn't work, it fails, we debug it, goes back, do it again. That process allows us to build amazing things. So this is, for example, one of my projects. You can see all the white stuff is basically 3D printed. This is actually a 3D printed launch stand on I think it was a $25 Amazon Music stand that's attaches the rail directly to the, and then the rocket itself was designed to fly small electronic payloads. We'll see more in a bit. Electronic drag, so I can get the maximum altitude and the least propellant. So not only does the 3D printing allow me to make it cheaper to start with, it also allows me to fly it for less money for each flight. So this is the S4 satellites. I'll mention this again. This is also the unique combination of 3D printing to make the package, plus the electronics inside that shrink a lot of function to a very small space. Fiberglass body tube, using standard off-the-shelf avionics, 3D printed nose cone, and then it flies. And what I found interesting is that I could actually now 3D print a flyaway launch system that works, as you see, pretty well. So this is another project, which is a 54 millimeter. I think it was the big daddy of that. It's optimized for performance. It has a power series nose cone for minimum drag in the flight domain in which it flies, which is generally Mach 1 to Mach 2. It flies with a whole bunch of avionics in the nose cone. So off-the-shelf Telemega and Easy Mini for flight control. But I had made my S4 project for collecting data. In particular, my goal here is to get through of what the nose cone temperature really is. I believe somehow that in that flight regime we need aluminum nose cones. Fiberglass airframe with a minimum aluminum motor retainer. All the parts you see, well, the fin can, recovery system, the nose cone, the ab bay, flyaway launch system are all 3D printed. And this looks, pandemic has limited my testing, but I'm enthused that it will go really fast and really far. This is my big project, which I mentioned, which replaces that big red and black monstrosity. So this is designed to fly 2 1U CubeSats or 1 2U CubeSat, like you'd fly an ARLISS or SLI or the 10,000-foot SA Cup airframe. And fiberglass airplane with a motor controller. All the white stuff you see is 3D printed in PETG. And it has a regime in the transonic range of 0.8 to 1.3 Mach. And you can see on a K550, it takes us to SLI altitudes of about a mile. And then on a M1315, it takes us to SA cup altitudes for about 10,000 feet. But there, it will fly, because it's light, it can fly on these very long burn motors like the M650 and the M685 that will give glorious 10-second burns on this, which I anticipate, I'm looking forward to a lot. So I argue that 3D printing is now the new standard, particularly for small airframes, for mid-power. TARC, my 3 TARC teams are all doing that. I think we now, up through K and M, we can do lots of parts. And we do avionics and recovery parts for very high performance. And I think in certain special cases, we're doing a prototype on a 2-stage O to M rocket that will be the interstage, printed in nylon plus embedded carbon fiber. I'd now like to transition to the other revolutionary technology that I think combines with this to make this a turning point in amateur rocketry. And it's motivated, I say euphemistically, by Moore's Law. I don't know how many of you know Moore's Law, but it is, we've taken it for granted for the last 50 years. And it's pretty amazing. So this is the chart. This is a linear time chart on the x-axis. On the y-axis, it's an exponential in transistor count, or pardon me, logarithmic scale in transistor count. And what we can see is that roughly about every 2 years, we can put twice the number of transistors in the same space for the same price, which means that cost roughly decreases in half every 2 years for the same number of function, or function doubles, or power decreases, because actually smaller transistors consume less power to switch. So the key issue is that we are on a course of having amazing functionality at very low power available to us to do quite amazing things that we couldn't do previously. So key influence here, what can we do with software now? Because now what it means is that we can run very powerful software on amazingly small things, enabled by, which gives us yet more sensors, which have with some amazing transitions, pardon me, things happening in technology, particularly about communications. So let's talk about software. Because we have so much power, even in very small processors, we now can program in very portable high-level programming languages that are portable between architectures, between systems, and we can now make very interesting choices about picking which processors because of the how fast we need to process things. So today, almost any of the processors I'll talk about, you can program either in Arduino, it's C and C++, or in Python, which is a more powerful language in some sense, denser code, less lines, doing more function, albeit I think it's materially slower, particularly for real time, that we see in many of our projects that will look at satellites or doing avionics. The good thing about them, both have now huge libraries of open source algorithms. You can get open source for doing Kalman filters for processing real-time data. You can get imaging things. It's just an astonishing collection. And for almost all the sensors we'll talk about, there are libraries available, so you don't have to do that. So it's easy as plugging things together and then getting the right library and doing the integration. So the level of difficulty has reduced dramatically to build really amazing things. So we have and then it extends to operating environments. We can build very simple programs that are simply linear, maybe a giant for loop or a giant while loop, just essentially polling. Or, as I've begun to adopt, we can make complex real-time systems using off-the-shelf open source real-time operating systems like FreeRTOS, which I like a lot. Or we can actually, if we go a little bit bigger, we can actually run Linux. I want to start talking about processors in a slightly different way. So I began my career doing security software for the early in mid-70s. I inherited a lab, and the lab that I inherited was running a PDP 1145. Some of you may be old enough to remember PDP 1145s. And we were lucky enough to have the first Unix, one of the first Unix v6. And our job was we were actually re-architecting Unix to essentially add security to it. So in 1975, I had a PDP 1145, and it occupied half a room. It was big, had a need special air conditioning. This processor, which is an inch, inch and a half by less than an inch, it's 1.3 by 0.7. It's a single core ARM processor at about 120 megahertz with hardware floating point. This has more memory and is about 5 times faster than that PDP 1145. If this had the option for having memory management, we could run Unix on this or Linux. It has, I want to particularly point out the I2C port, which is now great for, is almost every sensor we want to imagine has an I2C connector. We can daisy chain them together, and it even removes the hard part of doing the wiring because they just plug together with standard connectors. I run it with FreeRTOS, and I run it, because I'm old, I run with C++, but it also runs Python. For my younger students, are all being trained on Python. It's $15. We can then shrink that to about half the size. This is a different version of an ARM processor. It has actually more memory. It actually has built-in Wi-Fi. And it also runs C++ and Python, and it has less connectors, so it can do as more of a problem doing more peripherals, and it's cheaper at $10. I use this for smart daughter boards to run smart peripherals. Like I have one of these that connects to one of the peripherals we'll see next, which is a gamma ray radiation sensor. So this drives the gamma ray radiation sensor and then collects it and sends it over I2C to the processor in the center, which acts as the master processor for the satellite. And then lastly, we have our new version of the Raspberry Pi Zero. This is the version 2. It's a quad core. It's 4 processors at 1 gigahertz. It's a bit bigger. It's about twice as the footprint that you see of the Itsy Bitsy. This is probably too big to fit in some of my satellites. And but it runs native Linux, and you can program it in a language of your choice, and it's also about $15. We have enormous capability here that essentially replicates in a couple of my fingers what I used to take a room size when I started my career. Sensors has gone off the hook with more sensors than we know what to do with. For example, this is a wonderful little CO2 sensor. I believe it's $30, but actually measures real CO2 levels. So we can fly this through the atmosphere stack, and we can monitor the levels of CO2. So this allows students to essentially make direct experiments on the nature of climate change, of the nature of the atmosphere. This measures gas temperature and pressure. So this is a version of a GPS, though this is my personal favorite, but the one I got a picture of. But we can now have a GPS flying my little satellites. Will go up to 250,000 feet, and are pretty good against G load up to about 4G. And then they recover. This is one of my favorite processors. This was made commercially to sit in air quality sensors in people's homes, but it works really well to fly in rockets. And what it measures is it creates a histogram, essentially a spectrograph of the size of air particles. So it essentially says what air particles are what size. So we can imagine flying this again on a payload and essentially doing a vertical cross section of what atmospheric pollution looks like. This is actually my favorite sensor. This was made after Fukushima by a German semiconductor company, and it's actually a small gamma radiation sensor, and it has little flashes of light inside that is measured by a little photodiode, and that gets converted into a pulse that we can then measure. That pulse tells us the size of the gamma ray and its energy. This is, I believe, $60. And then last, we have way too many sensors for measuring attitude of things. So 3 dimensions of acceleration, of vertical acceleration, 3 dimensions of spin, basically, along the 3 axes, and 3 dimensions of measuring field. Can make essentially positioning systems. Communications happens to be my particular forte, and one in which I have a lot of expertise. And wireless communications is a necessity in my mind in rocketry. I'm getting old enough now that I can't see things, so I really need to track things electronically and have my rockets tell me where they are. But I'm also fascinated by the ability of my rockets to go places and tell me about the experience, which means I need the telemetry. The legacy for the last, 20 years has. So I show one of my favorite products, the Big Red BB line, which is running at 70 centimeters, and the ground station for it, which is in my case a Yaesu APRS. And the standard for the last almost 40 years called APRS, which is a telemetry standard designed by hams. It's used widely by ham sets and any universal ham sets. Arguably, it's one of the standards for building CubeSats. But we're at the edge right now that we can replace a lot of this. And I show a little picture in the corner of my new favorite. It's greatly enlarged. Think about that device you see there as the size of your fingernail. And let's see what we can do. That implements a new standard called LoRa. LoRa was invented for the long-range Internet of Things, meant to be very low power. And you can see in this chart, though the axes are kind of bad, the vertical axis is meant to be bandwidth, while the horizontal axis is meant to be range. And LoRa is an interesting standard that is designed to do very long range and lower speed, exactly what we need for telemetry. And I think it minimizes how good LoRa really is. I got introduced to LoRa about 7 years ago, and came across a blog by a guy in the UK who was tracking his high altitude balloon. His balloon was over Czechoslovakia, about 400, 500 kilometers away. And he was in a pub with his laptop at a little ground station, drinking his beer on his laptop, tracking his high altitude balloon 400 kilometers away. And I said, well, that's interesting. And if you can do that with a device that's the size of your fingernail, well, that gets even more interesting. So it turns out that LoRa was a standard originally invented by IBM in Switzerland. It's now been brought into the US and owned by other companies. Microchip is one of the major vendors of building. It's inexpensive spread spectrum radio designed for long range and low power. It can dynamically tune, trading off through about 300 bits per second to 30 kilobits per second against range. So at lower speeds, you get longer range. Higher speeds, you get shorter range. And what it does really is take advantage of spread spectrum to dramatically increase receiver sensitivity. I'm not going to go through in detail and bore everybody, but it's a clever, very, very compelling design. And it's $5 and the size of my fingernail, and it's a fully packetized solution. So it directly connects. You basically give it a packet, say send it, wait for it to receive it. It's a smart little peripheral, much like a $5 little Ethernet connector that's designed to be wireless over 400 kilometers. So how do you use this stuff? And what does it mean? So the big market for this stuff is really the Internet of Things, particularly power meters. Just an example of gas meters, utility meters that are being deployed in millions across the world, using this technology to collect data and to reprogram power use in real time. It's also used in rocket tracking. So if any of you have used the Featherweight GPS tracker, it's the communications chip that's used there at 900 megahertz. The chip comes in various varieties. I happen to use the one in the ham band at 70 centimeters, 130, 150 megahertz. It goes a little farther. The lower the frequency, generally the greater the distance you go. And then it's used the satellites. Did in my satellite in 2017, the one with the check mark. The first satellite, I believe, that got LoRa packets out of orbit. I didn't get many, The satellite failed after a few orbits, but I did get a couple of packets. And then I implemented it in my little student satellites called S4, which is that's a 5 centimeter cube that you have two PC boards of 42 millimeters. That this has GPS, 9DOF, attitude, pressure, temperature, and telecommunications all built in. Kind of cool that I put this up. A team of high school students out of Spain. You can see the leader of the team there holding up his satellite, which is a 1P pocket cube, the same size as called FOSASat. They've now incorporated, they're building a business out of this, building much larger satellites. And one of the cool things they did was to build a network, a distributed network of small ground stations. You can see one here. It's about the size of a package of, and they build these things all over the world. They built a network of 400 ground stations connected together with the internet. So as their little satellite passes over, one or more ground stations can pick up the telemetry. So basically, these little $5 part can do telemetry from low Earth orbit, as well as to our rockets. So what can we build out of this combination of technologies? Well, first of all, we can build cool 3D printed packages. So below you, the grill out, the fireplace out there is decorative. On the left, you can see a 2U CubeSat, the structure of a 2U. So it's 20 centimeters by 10 by 10. And then next to it, the little black frame is a 1U CubeSat, which is 10 centimeter cube. And lastly, is a 1P pocket cube, which is 5 centimeters. So 20 years ago, when Bob Twiggs invented CubeSats, the size of it was the one in the middle, or more likely the one on a 2U. The functionality that 20 years ago that we thought we could put in a 1U, we can easily put into a pocket cube today. So pocket cubes, mass and volume are everything in rocketry. So if we can make things smaller, we can put more of these things up at once. And then we can build things inside them. So here are those processors I mentioned with a 1P pocket cube. You can see the little radio over there and then the processors. So we can build amazingly functionality. We have things running Unix here and sending real-time telemetry in the size of something that you can hold in your hand. And the cool thing is, this is actually the two boards of a S4. It's getting twice as better roughly every 2 years. What that means is we generally get more power, probably less power consumption, which means longer battery life, and more processing speed, so we can take on more complex algorithms and process it locally and take advantage of cheaper telemetry to send a little bit less data because we've processed it locally, essentially processing it at the edge. So I want to talk about two projects that I've involved in that implement all these pieces. So the first of those implements that thing I saw before, which is the pocket cube. So I call it S4, and it's a derivative of the ARLISS program. So in essence, you can see in this picture an old technology of doing CanSats, a CubeSat, which is a 10 centimeters, then 5 centimeters. Why would anyone want to do a CanSat anymore? Bob Twiggs, by the way, invented CanSat, so he knows that I like this idea of obsoleting things. So basically, things like pocket cubes are the new CanSats. And I give a link to here to build these things if you want to build them. So you can build high performance, a low cost science payload that has telemetry that will reach to orbit, that has a high speed processor that runs C++ or Python, and more sensors than we know possibly to do with. And so our challenge right now is to think about science experiments that allow us to investigate using these for rockets. You can build them on this kind of system. You can fly it in your park up to 3K at your local launch, or flown them up in sounding rockets up to 150K on ARLISS Extreme. And as our friends in Spain did, fly them to LEO. He went up in November 2019 on a Rocket Lab's Electron. It's always good. Rocket. That was the mandatory rocket flight. The second project I want to talk about is a project I'm doing with a team of high school students in Virginia. And what we're building is a 2U CubeSat implementing a technology called acoustic levitation. Now, this diagram on the right, on the left, is kind of the prototype. It was designed by a University of Bristol, a team of physicists there. And what it does is create two phased arrays. You can see a top array and a bottom of ultra-acoustic transducers. Those phased arrays create a focused beam of sound waves. And you can then control it, in this case, by an Arduino, and then we control the Arduino in turn by a Raspberry. And we can essentially suspend a little styrofoam ball, and we can move it up and down. So we have unidirectional control, hands-free, of moving something in space. And on the right, see an illustration of what the focused sound waves does, the combination of the shaping of the two arrays of transducers, as well as the frequency in which we are emitting the ultrasonic wave, which is 40 kilohertz. So this is it incorporated into a 2U CubeSat. Allows us to think about the hands-free manipulation of objects via paired phased arrays of ultrasonic transducers. It turns out 30 years ago on the ISS, it was not particularly inexpensive. But now this will cost us about $100 to construct after we finish prototyping. And this competition sponsored by the AIA for a high school project. It's going to be flown on New Shepard in mid-2022. And one of the things that our students are adding is they've added a Raspberry Pi that controls the transducer, as well as a little AI controlled camera called a Pixie Cam. So we're doing AI or image recognition of where the ball is, and then using that as feedback to change the frequency of the phases of the phased array, so that we can essentially demonstrate moving the ball in microgravity. It's going to be pretty cool. It's in development right now. So these projects, these small satellites, are not possible really at any reasonable cost point unless we have this amazing intersection between amazing and amazing 3D printing. And I encourage you to think about doing your own projects like these that challenge yourself, your students, your friends, or your children. And I'm going to stop here and look for questions. I was asked about a part number for the air particle detector. It's an Adafruit product, and there are about 3 different versions of it. So I would just go to the Adafruit website, and it's easy to find. The one I showed is the one I particularly like because it has an I² detector, and there's a good set of libraries both in Python and in C++, Arduino, to collect data from it. It probably doesn't do better than about 1 hertz in terms of data collections, but clever little product. It gives you a histogram of about 5 different particle sizes. I remember about 3 or 4 years ago, I was at SLI, and there was a high school team there that had tried to do it. Their mentors had tried to build a similar thing using a green laser and imaging and a system that was about this big that they tried to work and didn't work, and the students could. So, but here now for, I think it's 30, 40 bucks, something like that, that can actually give us a very detailed measurement of what air pollution looks like. Any? I hope I haven't bored you, and I hope I support SLI, Student Launch Initiative. NASA has a project that university students, but the top 25 competitors out of TARC can also apply. And it's basically a school year long program. You apply roughly in September and you finish roughly in May. And you work with NASA engineers that are actually presenting a problem. They want you to fly generally a mission with some kind of payload. Design the mission, you probably decide the payload and design the rocket. And you then go through a series of document NASA-like program management issues like PDRs and CDRs that we would see in more complex aerospace projects. And they then fly them in Huntsville, Alabama in early April, roughly to about 5,000 feet. And the students spend the week basically touring the NASA facilities at NASA Marshall. It's really a truly amazing experience. When we're able to have it in person again, and I believe it's targeting this year to fly in person again. It's always a thrill for me to go back. I help the project, and the final celebration and award giving is held in this huge building, which holds one of the last real Saturn V's. So it's suspended in the ceiling above you, and you get to have dinner underneath it, and it's really quite cool. Anything else? Well, if we're done, I will let the class go home early, and we'll take advantage. It's actually a pretty nice day out here today. So I'm in California, I'm in Oakland, and yes, get a late lunch and enjoy the day. Thank you very much for listening. I hope you're inspired. I hope you go do cool things. Thanks a lot. Bye-bye.